We have made it to Unit 5, and in Unit 5 we are going to discuss systems of equations, in particular systems of linear equations. So what I've written here are two linear equations. The first one, x minus y equals -4, and the second one, 2x plus y equals 7. These are both equations of lines, and together the pair of equations makes up a system of equations. For the purpose of our course, we'll be looking at two equations that have two variables, and we're going to try to solve for those variables. So a solution of a system of equations in two variables is an ordered pair of numbers that satisfy both equations. So the ordered pair is an x value and a y value that when we plug it into both equations hold true. One example of a type of problem you might see with systems of linear equations is this type. Determine whether an ordered pair, in this case 1, 5, is a solution of the system above. So we're going to take this ordered pair and we're going to test it to see if it's a solution of this system of equations. In order to do that, I'm going to look at my ordered pair, and the first value, the x value, I'm going to plug in for x in each equation. The second value in the pair, the y value, I'm going to plug into y in each equation. So here I've written out equation 1, x minus y equals -4. For x, I'm going to plug in my 1 from the ordered pair, and for y, I'm going to plug in 5 from my ordered pair. You'll notice that 1 minus 5 on the left-hand side equals -4, and that's on the right-hand side of the equation. So if we kind of plug in and then rewrite this equation, solving on the left, we discover that -4 is in fact equal to -4. Okay, I've kind of tested whether this side equals this side. That's why I have a question mark over this equal sign. Does this side, when I plug in these values, equal this side? And it does, in fact, so I've drawn a check mark. So I know my ordered pair satisfies the first equation. In order for the ordered pair to be a solution to this system, it also has to satisfy the second equation. So here I've written equation 2, 2x plus y equals 7. For the x, I've plugged in 1, my x value from the ordered pair. For y, once again, I've plugged in 5. So I have 2 times 1 plus 5 on the left, and I want to test, does that equal 7? And it does. 2 times 1 is 2, 2 plus 5 is 7. 7 equals 7, that looks great, another check mark. So because 1, 5 makes both equations true, we end up with true statements, mathematical statements, in each equation. This means that 1, 5, this ordered pair, 1, 5, makes both equations true. It is a solution to the system. In the last page of notes, we verified a solution to a system of equations. In this page, we're going to talk about one method you can use to find the solution yourself. This is the method of graphing. So you can solve a system of equations by graphing, and here's how you do it. You want to graph both equations and then identify any points where those lines, in this case, intersect. An intersection is a solution to the system. Since in this course we will only be dealing with linear systems of equations, you will have two lines and they will intersect maybe at one point, maybe at infinitely many points, maybe at 0 points, but we'll get into those complicated aspects a little bit later. For the most part, if you have two different linear equations and they're very different, they will intersect at one point, and that one point will be your solution, if you have one. So to find this solution to a system of equations by graphing, what I would do is I would first get each equation into a form that is easier to graph. I'm going to use the slope-intercept form. So I've written out equation 1 and equation 2, and I've rearranged each equation individually so that it is in slope-intercept form. The first equation, x minus y equals 1, can be rearranged by moving the x over to the other side of the equation. I will subtract it from both sides. I'm left with -y equals 1 minus x. Now I want the y by itself to be positive, so I will divide both sides by -1,
or you could multiply both sides by -1. We're just going to flip all of the signs, and I will be left with y equals x minus 1. And this is in the form y equals mx plus b, our slope-intercept form, where m is the coefficient on the x, that's our slope. In this case, our slope is 1. And our y-intercept, that is going to be the place where your line crosses the y-axis, is -1. That's b, this number right here. So I have my first equation in slope-intercept form, and I've identified the slope and the y-intercept, allowing me to graph this equation. I'll start graphing it by first plotting the y-intercept. The y-intercept is the point 0, -1. So the y value is -1, the x value is 0. So I know that this graph is going to cross my axes at -1. So I would plot a point right here. I also know that the slope is equal to 1. Slope is your rise over run, or your change in y over change in x. This means if I go up 1 unit and over 1 unit, 1 over 1, then I can draw another point on my line. So from my y-intercept, I'm going to rise 1 unit, go up 1 unit, and run 1 unit, go over in the positive direction 1 unit, and plot another point right here. Okay, and with those 2 points, I could connect them and draw this line, which is the graph of my first equation. You could also take this equation if you didn't want to use your slope-intercept form to graph. You're also welcome to just plug in values for x and see what y values you get, and then plot those ordered pairs and connect those. That will work as well. So whatever way you prefer to graph a linear equation will work just fine. The idea is that you need to get this line plotted on your graph. So for the second equation, I've started with x plus y equals 5. That's the original second equation in the system. And I'm also going to rearrange this one to be in slope-intercept form by subtracting x from both sides. That gives me y equals -x plus 5. This is in the form y equals mx plus b, where m, the slope, is -1, and b, the y-intercept, is +5. To graph this, I know it's going to cross my y-axis at the point 0, 5, when y is 5, so I would plot a point right here. And I know my slope is -1, so I'm going to go down 1 unit and over 1 unit. Down for the negative and then over. So -1 over 1 means the rise is negative, we're going down, and the run is positive, meaning we will go to the right. You could also think of this as a positive rise and a negative run. Remember, it doesn't matter in a fraction if your negative is on the top or the bottom. It still has the same value if there's a negative on the top or bottom of a fraction. So you can think of this slope as -1 over 1 or 1 over -1. Either way, you will be able to plot this line correctly. Once we have these two equations graphed, you will see that they intersect, and thankfully they intersect at a very nice clear point here. This looks like the x value is 3 and the y value is 2. So when x is 3, y is 2. That gives us an ordered pair. The graphs intersect at the point 3, 2, and we know that 3, 2 is a solution to the system. Okay, if 3, 2 is a point that is on both lines, then we know that 3 and 2 for x and y will satisfy both equations, making it a solution. Sometimes when we're graphing systems of equations, some funny things can start to happen that, might throw you for a loop. So we're going to take a look at some special cases and their graphs. The first one here, y equals 2x plus 3 and y equals 2x minus 1. If this is my system of equations and I'm asked to solve it by graphing, I'm going to look for a solution by graphing, I would proceed the way we did in the previous page of notes. It looks like these equations are both in the form y equals mx plus b already, which is great news. So we could plot them on our graph. Just moving quickly through this, the first equation has a y-intercept of 3, so I would plot a point here, and a slope of 2, or 2 over 1. So I would go up 2 and over 1 to plot my second point and connect them. To draw the graph of my second equation, 2x minus 1, I would plot my y-intercept, which is negative 1, and then once again I would go up 2 and over 1 because the slope is also 2 over 1. That would give me this point, and I would connect them to draw this line. Now you'll notice that these equations are, well, they have some similarities. They have the same slope. They do have different y-intercepts. And what you'll notice when we graph them is that we've graphed parallel lines, okay? They run perfectly parallel to one another like train tracks. And we know that parallel lines never intersect, ever. So these lines will go on forever in either direction, but they will never cross paths. No intersection means there is no solution. So it is possible to have a system of linear equations that has no solution. This is kind of like a trick question here. This system of equations doesn't have a solution. No solution exists. That's one special case. There is another special case where something else kind of funny happens. That is represented here in this example. 3x minus y equals negative 6, and 2y minus 6x equals 12. I'm not going to go through exactly how to graph these lines. What I would do is, well, you could put them in slope-intercept form and graph them, or you might recognize that this is a special case right away. Either way, I just want to talk about what happens when you get the graph of each of these lines on some graph paper. They are, in fact, the same line. Okay, if you were to graph equation 1 and you went through your routine and graphed it, and then you graphed equation 2, you would notice that equation 1 and equation 2 fall exactly on the same line. So I have one giant bold line here because there's one line right on top of the other. And what's happening here is that our lines are intersecting at every single point. And infinitely many points make up a line. So we have infinitely many solutions in this case. So if your two lines are graphing one right on top of the other, they're intersecting everywhere. And this means that this system of equations has an infinite number of solutions.
One of the ways you can recognize this special case before graphing is by noting that one of your equations is the same as your other equation except for a multiplier. So I've written here equation 2 is a multiple of equation 1. And what I mean by that is that you can get to equation 2 by multiplying equation 1, multiplying every single term in the whole equation by a number. In this case, that number is negative 2. So 3x times negative 2 would be negative 6x, as we see in the second equation. Negative y times negative 2 would be positive 2y. And negative 6 times negative 2 would be positive 12. So these equations are related by that multiplier, negative 2. And since that's the only difference between them, that will cause these two equations to graph on the exact same line. They are essentially the same equation. So we have a fancy way that we can write out this type of infinite solution, because even though we have infinitely many solutions, it doesn't mean that any pair of numbers in the world will work. It's a very special set of pairs of numbers. It's all of the pairs of numbers that fall on this line that continues to infinity, up and down in either direction. So our fancy notation for this set of infinite solutions is called set notation. And these curly brackets mean the set of. So the way I would read this, what I have written here, is this is the set of all ordered pairs x and y, so that 3x minus y equals negative 6. Another way to read it is it's the set of all ordered pairs x and y that satisfy this equation. So when you want to write out a set of infinite solutions, it will always start the same way. You'll have your squiggly brackets. You will always have x comma y in parentheses here, and this long line. Sometimes you'll see a colon instead of the line. And then you can write down an equation here. We tend to use the equation that doesn't have the multiplier, so kind of the more simple version of the equation. In this case, that's equation 1. So you can see I've written equation 1 here. Any ordered pair that satisfies equation 1 will also satisfy equation 2. So this set represents the infinite set of all solutions that satisfy this system of equations. At this point, we've identified 3 different scenarios that you might see when solving a system of equations by graphing. You might get 2 lines that intersect, in which case they will intersect at one point and you will have one solution, so one ordered pair of numbers that creates one solution to the system. You might have parallel lines that never intersect, meaning there is no solution to the system, or you might have lines that are essentially the same, graphing right on top of one another, that have this fancy infinite set of solutions. What I want to talk about next in the next page of notes is that we don't always have to graph to solve a system of equations. There are other methods at arriving at a solution that satisfies both equations. One method is the method of substitution. So I'm going to show you an example of how substitution works with this system here. Our first equation is 2x minus 3y equals negative 2. The second equation is 4x plus y equals 24. In order to solve this system, I'm going to solve one equation, any equation that I choose, for one variable, any variable that I choose. So I have a lot of choices here. Your solution might look different from mine, but you will end up with the same result. So you want to look at each of your equations and decide which one would be easier to write in terms of one variable, and which variable would be the easiest variable to solve for at first. So you can choose which equation to use, and you can choose which variable to use first. I like to take the easy road when I can, so I see that there's just a plain y here in the second equation, and that would be nice to solve for because it wouldn't require as much algebra to get this y by itself in this equation. So for this example, I'm going to choose to solve the second equation in terms of the variable y. When I do that, I'll have to subtract 4x from both sides, and I'm going to end up with y is equal to 24 minus 4x. I've chosen to rearrange the second equation in terms of y. Once I've done that, I now have a bunch of numbers and a variable here. This whole expression is a representation of the variable y. I can take this whole thing and treat it as one number, and I can plug this whole thing in wherever I see y in my other equation. So that's what's going to happen next. Whichever equation you chose to solve for, you're going to plug your result, this whole side of the equation, into the variable in the other equation. So plug this into the variable in the other equation. My other equation is 2x minus 3y equals negative 2. I've rewritten that here, and in place of the y, I've plugged in everything that y equals. Y equals this whole thing. So instead of y, I'm writing in parentheses 24 minus 4x. Everything else is just carried down from that first equation. Next, I'm going to, kind of simplify this. I want to solve for the variable that I have, and I still have the variable x sticking around, so I'm going to solve for the variable that's left. First, let me distribute this 3 to each of these terms here. Negative 3 times 24, that gives me negative 72, and negative 3 times negative 4x gives me positive 12x. The 2x is just carried down, it stays the same, as well as the negative 2 on the other side of the equal sign. At this stage, I have like terms, 2x and 12x. I can combine them to be 14x. The negative 72 stays, as does the negative 2. And now I can subtract, I can add 72 to both sides to get rid of the 72 over here. When I do that, negative 2 plus 72 is 70. I'm left with just the 14x on the left and a 70 on the right. Then I can divide both sides by 14. So 14 divided by 14 is 1. I'm left with just x. That looks good. And 70 divided by 14 gives me 5. So what I found here is that x equals 5. This is the first half of my ordered pair solution. So I know that my solution has to have an x value equal to 5. Now I want to find the corresponding y value. Here's another place where you can make a choice. You can plug the value you found, in our case x equals 5, back into either equation, in fact any equation we've used so far, to solve for the other variable. I could plug this x equals 5 into this first equation and solve for y. I could plug it into the second equation and solve for y, and I would get the same y value, the one that I'm looking for. I'm going to be extra clever, and I'm going to plug my x equals 5 into this modified version of the second equation because it's already solved for y and it will save me some work. So I'm going to take x equals 5 and plug this 5 in for x in this equation. This is my second equation written in terms of y. So what I've done here is y equals 24 minus 4x. I've rewritten the equation I'm going to use to find y. I've plugged in 5 for x, and then I've solved. So 4 times 5 is 20, so with this negative, it's negative 20. The 24 is still sticking around. 24 minus 20 is 4. So I found that y is equal to 4. Again, you could have plugged this x anywhere you see an x and solved for the y that's associated with whatever choice you have, but it might be worthwhile to try to make choices that save you a few steps. That is the nice thing about these problems. So I now have my x value and my y value, 5 and 4. That is my ordered pair and my solution to the system of equations. So 5, 4 is the solution to the system. This example was a case where we had two lines that intersected in exactly one point. You might be wondering what the system or the method of substitution looks like if you have one of the other scenarios that we talked about in the last page of notes. What would happen if we had no solutions or infinitely many solutions? How would that algebra look? Well, our next page of notes is going to address exactly that issue. We're going to have a look back at the special cases. So I've used the exact same systems that we used for the special cases for graphing, and I just want to show you what will happen if you attempt to solve one of these systems of equations by the method of substitution. So our first system that was a special case, y equals 2x plus 3 and y equals 2x minus 1. Well, to use substitution here, I get to skip my first step because my equations are already solved in terms of one variable. Okay, so I've already solved for y here and here. I don't have to do that step, which is great. What I can do is I can notice that 2x plus 3 is equal to y and 2x minus 1 is equal to y, meaning that I can plug either one of these in to y in the other equation. So what I've done here is I've taken this second equation, and instead of writing y on the left, I've written what y equals, 2x minus 3. I can set these guys equal to each other. 2x plus 3 is equal to 2x minus 1. That's my substitution. And now I'm going to attempt to solve for x. But what happens when you try to solve for x, you need to get both of your x's on the same side of the equation. You would subtract 2x from both sides. And the problem there is that your 2x's would cancel. 2x minus 2x is 0. So our x's go away, and we're trying to solve for x. I can't solve for a variable that has disappeared. So this is a problem. What happens when I try to solve for x is I end up with an expression that doesn't make any sense. I end up with 3 is equal to negative 1. And that's nonsense. It makes me sad, okay? This is impossible. Because we've ended up with a variable that disappeared and an equation that makes no sense, we know that there is no solution to this system. Another way to think of this is that no value of x or y could ever make this system true. We could plug in 27 billion for x and plug in 27 billion for x here, and they would still cancel out, and we would still be left with 3 equals negative 1, which doesn't make any sense. No matter what value of x is plugged in here, this is never going to create a solution. So when you end up with this type of scenario, it's safe to say that your entire system has no solution. There's another scenario that you might see. This is the scenario where you would have infinitely many solutions. And I will show you what happens when you attempt to substitute to solve this type of system. This system, 3x minus y equals negative 6 and 2y minus 6x equals 12. We can try to solve it by substitution by rearranging the first equation in terms of the variable y. So that's what I've done here in this step. I've written y equals 3x plus 6. That is the first equation solved in terms of y. Now if I took this 3x plus 6 and plugged it in for y in the second equation, I get 2 times y, which I've plugged in as 3x plus 6, minus 6x equals 12. And if I distribute this 2 to each term, I get 6x plus 12, minus 6x equals 12. And you'll notice 6x minus 6x, well, that disappears. Our variable has once again disappeared. But what we're left with is something that's true. 12 is equal to 12. And that's true, but there's no variable to solve for. We found something that makes sense, but we still have no value for x. We want to know what x equals. Well, this type of situation, where your variable disappears, but you're left with an equation that is true, means that there are infinitely many solutions. And those solutions take the form of our set notation, the set of all ordered pairs x and y, so that 3x minus y is equal to negative 6. Another way to think of this is that any value of x or y would make this system true, because the system is true independent of what the variables are. Okay, I could plug in any number for x here. I could plug in 42, I could plug in 12.7. It wouldn't matter because these variable terms are canceling out to give me a true statement. So all values of x or y that satisfy this first equation will make the system true. So the long story short here is, if you are trying to solve a system of equations by substitution, on the one hand, you might get a nice, neat, ordered pair, x and y. That would be your solution. But if, as you're doing your algebra to finish the substitution and solve, you end up with something that doesn't make sense, it's safe to say that the system has no solution. And if you end up with something that does make sense, but you still can't find values for the variables because they keep canceling out, then it is safe to say that your system of equations has infinitely many solutions. There is one more method that we can use to solve a system of equations, and this method is called elimination. Elimination is related to the substitution method because part of it works the same way, but it's kind of a little bit of a shortcut to get to the final substitution part. To show you what I mean, let's have a look at an example here. I have 2x plus 18y equals 10 and 3x minus 18y equals 30. If this is the system of equations that I'm looking to solve, then I can try to proceed at first by eliminating a variable. And this particular system is a very good candidate for the method of elimination because 18y and negative 18y will naturally cancel each other out if I add the whole top equation to the whole bottom equation. So what I've done here is I've added the equations. I've written a plus sign and a big equals bar. I'm going to add term by term the equations. It's important here that you have your x's, y's, and then your constants lined up so that you make sure that you're adding like terms. So 2x plus 3x equals 5x, 18y minus 18y, or 18y plus negative 18y equals 0. That has canceled out. We've eliminated one variable from the equation, and 10 plus 30 equals 40. What I found here is that 5x equals 40. I can divide both sides by 5 to find that x is equal to 8. So I have found here my x value, the first half of my ordered pair of the solution, very quickly. Now I can proceed by substitution. I can plug 8 in wherever I see x in any equation that I choose to use. I've chosen to use the first equation. I've taken my x equals 8, and instead of 2x, I've written 2 times 8 plus 18y is equal to 10. And then I can solve this equation with my x plugged in. I can solve this equation for y and find the second half of my ordered pair. So 2 times 8 is equal to 16, plus 18y is equal to 10. I can subtract 16 from both sides, leaving me with a negative 6 on the right-hand side, and my 18y is still hanging out on the left. Now I can divide both sides by 18. That leaves me with y on the left and negative 1/3 on the right. So my y value for my ordered pair is negative 1/3. 8 comma negative 1/3 is the solution to the system. Sometimes the method of elimination will not run so smoothly right from the beginning. There's kind of a case that looks like this. This next example, 2x minus y equals 9 and 3x plus 4y equals negative 14. In this case, you'll notice that we don't have matching coefficients on any terms, okay? 2 and 3 aren't going to cancel out. Neither is negative 1 and 4, and neither is 9 and negative 14. So what I would need to do is create some kind of modification so that I have a variable that gets eliminated when I add the equations. Here, again, you can make a choice. You can decide to eliminate the x variable or the y variable, but I like to make the choice that will make my life the easiest. So I think I'm going to try to eliminate the y variable because I can easily make this negative 1 a negative 4 if I multiply the whole top equation by 4. So what I've done here, you're going to multiply one equation by a constant so that one of the variables will eliminate. I've multiplied the first equation by 4. So in this first step, I've just written the first equation with a 4 out front that he's going to multiply by the whole equation, and I've just carried down my second equation. If I multiply the first equation by 4, I get 8x. 4 times 2x is 8x. 4 times negative y is my negative 4y. 4 times 9 is 36. And then I've carried down my second equation. Here I have my modified system of equations. Okay, I haven't changed the first equation because I've multiplied this guy by every single term on either side of the equal sign. So this equation, although it looks different, is actually equal to our original equation 1. Once I have this new modified system, you'll see that I can add them and that the y terms will cancel out. So if I add this equation to this one, 8x plus 3x is 11x, negative 4y plus 4y is 0, and 36 minus 14 is 22. 11x is equal to 22. I can solve for x by dividing both sides by 11, and I find that x is equal to 2. From here, you can proceed the same way we did in the previous example. You can plug this x equals 2 back into any equation or modification of an equation that you choose. I'm going to decide to plug this x equals 2 back into my second original equation. 3x plus 4y equals negative 14. So I've written 3 times 2 in place of the x, plus 4y equals negative 14. 3 times 2 is 6. The rest has stayed the same. I can subtract 6 from both sides, leaving me with 4y equals negative 20, and then divide both sides by 4, leaving me with y is equal to negative 5. So at this point, I've found my value for x and my value for y, and I can use them to create my ordered pair to negative 5, which is the solution to our system of equations. So just to recap, when you're using the method of elimination, sometimes you get lucky and you can proceed right to your addition step, and one of the variables will naturally cancel when the coefficients are the same number with different signs. Sometimes you won't have any matching coefficients with different signs, so you'll have to create them by multiplying one equation by any constant that you choose. From here, once you've eliminated a variable, you can solve for the other and then plug it back in to find the other. So in this way, it's very much related to the substitution method, but it might be able to save you a little bit of time if you try this one. This brings us to our final page of notes for Unit 5, where I will have a look at a word problem that uses a system of equations. So word problems are always very intimidating because there's a lot of words, and first of all, you have to interpret what's going on and what kind of solution you need to try to build. So I do want to have a look at this word problem, but I want to kind of express to you from the beginning that since this word problem is appearing in the system of equations unit, you can kind of have a clue that you're going to need to create your own system of equations with the data in the word problem. And once you've created that system of equations, you can solve it by any method that you like best. The system of graphing tends to not be the best method for solving systems of equations that you've built out of word problems or real-world applications, because oftentimes we're dealing with decimal points or strange numbers that will not graph as nicely as the practice problems that we used for our graphing method. So you might want to keep that in mind. But without going into any more of that, let's just go ahead and have a look at this particular word problem. It says, a pharmacy charged $35.85 for a brand name prenatal supplement and charged $30.34 for the generic version of the same supplement. If the pharmacy made a total of $1,721.24 off of the sales of these supplements, having sold 50 of them combined, how many supplements of each type were sold? This is a very intimidating looking problem. When I tackle word problems, I like to write down the numbers in the problems and then what they represent to me. So $35.85, this is the price for a particular supplement. And $30.34, that is the price for a different version of the supplement. So what I've chosen to do in my writing here is I've chosen letters for my variables. I've used A and B. You can use X and Y or any other letters that you'd like. So I will say that supplement A costs $35.85 and supplement B costs $30.34. I know that the pharmacy made a total of $1,721.24. So this number I can write down as my total sales number. And then 50, this number 50 represents the number of supplements sold. So it was the number sold, not dealing with the prices, but the quantity. So what we can do is we can build a system of equations with these numbers that we've been given. Our first system will represent the pricing of the supplements as they were sold. I know I had sold however many of supplement A, that's what I'm trying to find. This is my quantity of supplement A, and each one of those costs $38.85. So for each one of these, I have to multiply that by the price. Okay, so if I had one supplement A, that would have cost $38.85. If I had two, it would have cost double that, 3, triple, and so on. That's why we're multiplying here. We multiply the number of supplement A sold by the price. We're going to do the same thing with supplement B. We want to multiply the number of supplement B sold, which we don't know yet, by the price of supplement B. Once we've multiplied each supplement quantity by its price, I know that the total of those values, of those sales values, will equal the total sales, which is $17.21.24. So however many of supplement A at this price, plus however many of supplement B at this price, somehow all of that equals up to the total sale price. The total sales that the pharmacy made. That's our first equation. That's one equation with two variables. So we'll need a second equation so that we can solve for both variables. The only other information that I haven't used yet is this number 50. I know that 50 is the total number of the supplements that were sold combined. So I know that however many of supplement A were sold and however many of supplement B were sold, together those amounts equal 50. This gives me my second equation, A plus B equals 50. Setting up a system of equations from a word problem is by far the toughest part of these types of problems. And I can tell you right now that the ones that we will look at will follow certain patterns. So if you get some practice setting up these problems, they will always work in very similar ways. You will always have multiplication and addition in your first equation. So you'll have a number times a quantity that you're looking for, that's a variable, plus a number times a quantity, that's your second variable, and then some kind of grand total. And then you might have the total for your quantity numbers together, and that will create your second equation. So there's some intuition involved here. I invite you to kind of, try this word problem on your own a couple times and make sure you understand where each number from the words is going into the equations and how we've written this mathematical representation of these paragraphs. So from this point on, we do have some crazy decimals and some strange looking things, but this is just a system of equations like we've solved in the previous pages of notes. So I've decided to use the method of substitution because I can very easily solve this second equation in terms of one variable. So I've done that here. I've taken the second equation, A plus B equals 50, and I've rewritten it by subtracting B from both sides, and I've gotten A is equal to 50 minus B. Now I've written one equation in terms of one variable. So I know A is equal to 50 minus B. I can now take this 50 minus B, which is A, and I can plug it in where I see A in the other equation, in this case the first equation. So next I've rewritten down the first equation, 38.85, but instead of writing A, I've written what A is, 50 minus B in parentheses. Then I've proceeded to write the rest of the first equation. Now I'm going to simplify and try to solve for the variable that I see here. I'm going to simplify and try to solve for B. First, I'll distribute 38.85 to the 50 and to the negative b. What I get is 1942.5 minus 38.85b. And I still have my plus 30.34b, and I still have my grand total here on the right-hand side. Next, I will notice that, let's see, I have like terms here, 38.85b plus 30.34b. I can combine those to equal negative 8.51b. I've just carried down my other numbers in the equation. And from here, to get the b by itself, I'm going to subtract 1942.5 from both sides. And that leaves me with this 8.51b and negative 221.26 on the right-hand side. To get b all by itself, I'm going to divide both sides by negative 8.51, leaving me with b is equal to 26. So now I have found the value of one of my variables. This happens to be the second value in my ordered pair. I know that b is equal to 26. Now I can plug that in to either equation to find a. Now I'm going to plug this into the second equation because the second equation is much easier to use than this first equation with all of the decimal points. So I'm going to take this b, 26, and I'm going to plug it in where I see b in the second equation. In fact, to make this even easier, why don't I use the modified version of the second equation, which is already solved for a. No need to solve for a twice. So I will plug in b where I see b here. A is equal to 50 minus 26. 50 minus 26 is 24, so I know that my a is equal to 24. A is 24 and b is 26. This is my ordered pair and my solution to my system of equations word problem. 24 brand name and 26 generic supplements were sold at the combined total sales price of $17,021.24. So we've successfully found the quantity of the brand name supplement as well as the quantity of the generic supplements that were sold, given the information that was provided to us in the word problem. So this problem brings Unit 5 and actually all of the course content to a close. So congratulations, you have at this point seen all of our course content for our term. So I wish you luck in your assignments and on your final exam.